In this video we are going to talk about a class of functions that are called generalized hyperbolic functions. We are going to define these functions and discuss some of their properties. The sine hyperbolic alpha t is a to the power of t minus a to the power of minus t over 2. Cos hyperbolic a t is a to the power of t plus a to the power of minus t over 2. Tan hyperbolic of a t is sine hyperbolic of a over cos hyperbolic of a. Sine hyperbolic of a is given by this formula here. So we're going to take the quotient of sine hyperbolic of a over cos hyperbolic of a. And this is gonna be a to the power of t minus a to the power of minus t over 2 times the other fraction flipped, a to the power of t plus a to the power of minus t. So tan hyperbolic of at is a to the power of t minus a to the power of minus t over the exponential sum. Here a belongs to this interval from 1 to infinity. That's an open interval, doesn't take the value of 1, is greater than 1, this parameter a. And cotan hyperbolic of a is the other way around, cos hyperbolic of a t over sine hyperbolic of a t. So that's a to the power of t plus a to the power of minus t over a to the power of t minus a to the power of minus t. And here t is can take all the values of r except 0. Okay, so let's say that we want to take the derivative of sine hyperbolic of at. That's the derivative of this expression. I can differentiate the numerator and I will get a to the power of t ln a, and the differentiation of the other function, the second term, is gonna be plus a to the power of minus t ln a divided by 2. So from here that's ln a times a to the power of t plus a to the power of minus t over 2, and that is ln a times that part is cos hyperbolic of a. Now if I want to take the derivative of the cos hyperbolic function of cos hyperbolic of a t, that's taking the derivative of a to the power of t plus a to the power of minus t divided by 2, and that is going to give me a to the power of t ln a minus a to the minus t ln a divided by 2. I can take a common factor ln a, which is the natural logarithm, and inside the brackets I have a to the power of t minus a to the power of minus t divided by 2. So that's natural logarithm of a times sine hyperbolic of at. The derivative of tan hyperbolic is taking the derivative of sine hyperbolic of a over cos hyperbolic at, and we are going to use the rule for the quotient. So it's going to be the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, and divide by the denominator raised to the power of 2. So the derivative of sine hyperbolic we have showed before is cos hyperbolic, with the cos is going to be cos hyperbolic squared, and natural logarithm of a minus ln a sine hyperbolic a squared. And here we divide by the cos hyperbolic a to the power of 2. I can take a common factor, and I have ln a times cos hyperbolic a squared t minus sine hyperbolic a square of t over cos hyperbolic a squared t. That's gonna give me, the numerator is gonna be 1. So the derivative of tan hyperbolic a t is gonna be ln a. It's gonna be ln a over cos hyperbolic a squared t. And if you want to take the derivative of the cotan hyperbolic, that's the derivative of the cos hyperbolic a over sine hyperbolic a, and again we apply the quotient rule, so it's the derivative of cos hyperbolic a times the denominator minus cos hyperbolic a times the derivative of the denominator, and that's the denominator squared here. So that is gonna give me, I can take I can calculate the derivatives. The first one is gonna be ln a sine hyperbolic squared minus ln a cos hyperbolic a squared, and the denominator is gonna be sine hyperbolic a squared t. I can take a common factor minus ln a, and inside the brackets I have cos hyperbolic a squared of t minus sine hyperbolic a squared of t, and in the denominator I have sine hyperbolic a squared of t. This is an identity that gives me 1, and I will have minus ln a over sine hyperbolic a squared of t, and that's the final answer. Now about this identity, I can derive it simply by taking the definition of the functions. So I have cos hyperbolic a squared minus sine hyperbolic a squared of t, and that's a to the power of t plus 8 minus t over 2 squared minus a to the power of t minus a to the minus t over 2 squared. That is gonna give me a to the power of 2t plus 2 plus a to the power of minus 2t, and here I be careful with the signs. It's gonna be minus here, plus 2 minus a to the power of minus 2t, and the denominator is gonna be 4. So we can pretty much cancel this term and this term, this term and this term go away, and in the numerator we just have 4, and in the denominator we have 4, and that is 1. So the cos hyperbolic a squared t minus sine hyperbolic a squared t, this gives me 1. What is so special about this function is that if I take the expression sine hyperbolic at cos hyperbolic at tan hyperbolic and cotan hyperbolic and I plug in the expression a to b e, the Euler number, I go back to my hyperbolic functions. So these are called generalized because I can generalize for any base a. So if I plug a equal to e, then I go back to my usual hyperbolic functions.